3 weeks ago, this exact fault whispered. Tonight, it screamed. A magnitude 7.7 tore open the seafloor off northern Japan, the same trench, the same segment the one seismologists had already flagged as loaded and waiting. The same segment, by the way, that we covered on this channel 3 weeks ago and told you to watch. A tsunami raced towards shore, 172,000 people ran, and then Japan's Meteorological Agency did something it has done exactly 3 times in history. It issued a mega quake advisory, not a prediction, something arguably more unsettling than a prediction. Because what they're actually saying is this: they don't know if the worst is over, or if it hasn't started yet. Stay with me, because the data they're staring at right now tells a story that nobody wants to be true. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss a single update as this story continues to develop. Tell me in the comments where you're watching from, and tell me this. In the 15 years since 2011, Japan poured billions into early warning systems, rebuilt entire coastlines with seawall infrastructure, and trained a generation to run when the ground shakes. Tonight, the ground shook. People ran. And the agency watching this fault still cannot tell you whether what just happened was the disaster or the warning shot before the disaster. So did we learn everything from 2011? Drop that in the comments. Now, let's get into it. Part 1. The advisory that changed everything. At 4:53 p.m. on April 20th, 2026, the rupture began about 30 kilometers beneath the seafloor, roughly 120 kilometers off the coast of Iwate Prefecture. Within seconds, seismic waves were racing outward in every direction. The first P waves hit the coastline in under 30 seconds. The stronger S waves, the ones that actually shake buildings, arrived shortly after. And by the time the shaking reached Tokyo, 400 kilometers to the south, it had been detected, measured, classified, and broadcast by Japan's early warning system. The initial magnitude estimate from the United States Geological Survey came in at 7.4. That is a significant number. A 7.4 earthquake is capable of causing widespread damage, generating tsunamis, and killing people. But within minutes, Japan's Meteorological Agency, which has a denser and more sophisticated network of seismic instruments positioned directly above this fault system, issued a revised number. Not 7.4, 7.7. Now, if you're not a seismologist, that might sound like a small correction. It is not. Magnitude is a logarithmic scale, which means every full point represents roughly 32 times more energy released. A jump from 7.4 to 7.7 represents nearly 3 times the energy. And when Japan's agency revises a magnitude upward, it usually means one of 2 things. Either the rupture was larger than the first waveform suggested, or the rupture was slower and longer than a typical earthquake of that apparent size. Both possibilities matter, and we will come back to the second one because it is central to everything that happens next. But the magnitude revision was not the most important thing that happened in the hours after the shaking stopped. The most important thing was a document. A formal advisory issued by the JMA, using language so specific and so carefully constructed that most people reading the news headlines probably missed what it actually said. The Japan Meteorological Agency issued a megaquake subsequent quake advisory, and here is why that matters. This advisory protocol did not exist before 2022. It was created specifically in response to scientific understanding that developed after the 2011 disaster, when researchers realized that large earthquakes on subduction zones can be followed, sometimes within days, by even larger earthquakes on adjacent or overlapping segments of the same fault system. The advisory is not a prediction. Let me say that again, because it is the single most important thing to understand. It is not a prediction. It is a conditional probability shift. Here is what that means in plain language. On any given week in northern Japan, the background probability of a magnitude 8 or larger earthquake somewhere along this trench is roughly 1/10 of 1%. That is the baseline. The quiet hum of risk that always exists along one of the most dangerous subduction zones on Earth. After today's event, that probability has increased to approximately 1%. 1% over the next 7 days. Now you might hear 1% and think, okay, 99% chance nothing happens. That is technically correct. But it is also the wrong way to look at this number. What the advisory is actually communicating is that the system has moved into a different statistical regime. A tenfold increase in the probability of a catastrophic earthquake is not a small thing. It is the kind of shift that, in any other risk system we deal with in daily life, would be treated as an emergency. If the probability of a plane crashing on a given flight suddenly increased tenfold, that plane would not take off. If the probability of a nuclear reactor failing increased tenfold in a single day, the reactor would be shut down. We are not talking about certainty. We are talking about a system that just moved into a zone where, statistically speaking, the worst case is no longer a distant possibility. It is a close one. And the geographic scope of the advisory is not small either. It covers 182 municipalities, stretching from Hokkaido in the far north down the eastern seaboard of Honshu, past Sendai, past Fukushima, all the way to Chiba Prefecture on the outskirts of Tokyo. This is an area that contains tens of millions of people. It contains critical infrastructure. It contains the Fukushima Daiichi nuclear site. And for the next 7 days, every one of those municipalities is being told, in the clearest institutional language the Japanese government can produce, that the ground they are standing on is more likely to rupture catastrophically than it was yesterday. Is what happened today the main event? Or is it the foreshock? That question is not rhetorical. It is the exact question the advisory is designed to acknowledge without answering. Because seismology, as a science, does not yet have the tools to tell you, in real time, whether the earthquake that just happened was the release of stress or the beginning of it. That distinction becomes clear only in retrospect. And the advisory exists because retrospect is a luxury the residents of northern Japan cannot afford right now. The advisory is active until April 27th. 7 days, a window of elevated risk, a ticking clock on one of the most carefully monitored fault systems on the planet. And if you're wondering why, exactly, this particular event has the seismological community on edge, you have to understand one more piece of context before we go any further. This is not the first time this particular segment of the fault has spoken recently. It is the second. Part 2, the segment we flagged. 3 weeks ago, on March 27th, a magnitude 6.5 earthquake occurred in almost exactly the same location as today's rupture. The Iwateoki segment, the northern shoulder of the Japan Trench. At the time, it registered as a notable but not catastrophic event. Some shaking along the coast, no tsunami of significance, a brief news cycle, and then it was gone. But that earthquake should not have been forgotten, because the segment it occurred on had already been flagged, in the peer-reviewed literature and in agency hazard assessments, as a region of concern. After the 2011 Tōhoku disaster, researchers spent years mapping the stress changes that rupture had induced across the entire length of the Japan Trench. They used GPS data, seismic data, satellite observations, and what they found was that while the main fault segment that ruptured in 2011 had released enormous amounts of accumulated stress, the segments on either side had actually been loaded further. Not relieved, loaded. The Iwateoki segment, just to the north of the 2011 rupture, was specifically identified in multiple studies as a region where stress had increased rather than decreased. And in the years since, that segment has remained quiet, until 3 weeks ago, and now, until today. The jump from magnitude 6.5 to magnitude 7.7 is not small. Remember, magnitude scales logarithmically. A 7.7 releases more than 40 times the energy of a 6.5. So what we are looking at is not a continuation of the same intensity. It is an escalation, a significant measurable physical escalation on the exact segment that seismologists had already identified as the most likely candidate for the next major rupture along this trench. And this is where the central question of tonight's story sharpens. Is what happened today the main event, or is it the foreshock? Because if you are watching a segment of fault that has been flagged as stress-loaded for 15 years, and that segment produces a medium earthquake followed 3 weeks later by a large earthquake, the question you have to ask is not whether more events are coming. The question is whether the sequence is over. Faults do not rupture randomly. This is one of the most important concepts in modern seismology. Fault systems fail in structured patches. Each patch has its own geometry, its own stress history, its own frictional properties. When a patch fails, it releases stress locally, but often transfers stress to neighbouring patches. Sometimes that transferred stress stabilises the system, sometimes it destabilises it. And along a subduction zone as complex as the Japan Trench, Predicting which of those outcomes will happen is, frankly, beyond the current capabilities of the science. What we can say is that the Iwate-oki segment has now produced 2 events in 3 weeks. We can say that the second event was more than 40 times more energetic than the first. We can say that this segment had been identified, well before today, as a region of elevated concern. And we can say that the advisory the JMA just issued is a formal acknowledgement that the system is not behaving like a system that has finished releasing stress. 3 weeks ago, this fault whispered. Today, it moved. And the question that nobody can answer yet is whether tomorrow it will speak. One of the strangest things about today's rupture, and one of the reasons scientists are not treating this as a routine event, is that there were no clear precursors. No foreshock swarm in the hours before the main event. No obvious build-up. The fault went from quiet to catastrophic in a matter of seconds. This is not unusual for large subduction earthquakes. Many of them begin without warning. But it is a reminder that this system does not give us the kind of signals we would need to feel confident that the sequence is winding down rather than ramping up. And if this is part of a sequence, we need to understand what kind of sequence we might be in. Part 3. What the tsunami didn't do. The tsunami warnings went out within minutes of the rupture. Japan has the fastest tsunami warning system in the world, built directly on top of the lessons of 2011. Sensors on the seafloor detected the displacement. Computers ran the models, and the warnings hit the coastline before the water did. The initial forecast was serious. Waves of up to 3 meters were expected along the Sanriku coast. That is a wave tall enough to wash through the ground floors of buildings, tall enough to sweep cars off roads, tall enough to kill. Evacuation orders went out immediately to coastal communities from Aomori down to Ibaraki. Trains were stopped, highways were cleared, people moved as they have been trained to move to higher ground. But when the waves actually arrived, they were smaller than forecast. At Kuji, in Iwate Prefecture, the maximum observed wave height was 80 centimeters. At Miyako, 40 centimeters. Most other coastal stations recorded readings in the 20 to 40 centimeter range. Nothing close to 3 meters. Nothing close to the disaster the forecast had prepared for. You might read that and feel relief. Most people would. And relief is a reasonable response to the news that the tsunami was not what it could have been. But if you are a seismologist, relief is not the word that comes to mind when the tsunami is smaller than expected. Concern is the word. Because the size of a tsunami is not determined by the magnitude of the earthquake alone. It is determined by how much the seafloor moved vertically. And a magnitude 7.7 earthquake that produces only 40 centimeter waves tells you something very specific about where, exactly, that earthquake happened. The leading interpretation from early analysis is that today's rupture was relatively deep. The hypocenter was around 30 kilometers below the seafloor, which in subduction zone terms is well down the fault interface. Deep ruptures tend to produce strong horizontal shaking, but less vertical displacement of the seafloor, and less vertical displacement means less water gets pushed up, which means smaller tsunamis. Is what happened today the main event, or is it the foreshock? This is where that question starts to take on a very specific shape, because there is a category of earthquake known to seismologists as a tsunami earthquake. And tsunami earthquakes are not defined by how big they feel on land, they are defined by how big a wave they produce. A tsunami earthquake is a relatively slow, relatively shallow rupture that generates disproportionately large waves. You barely feel them, but they can kill tens of thousands of people. The classic example is the 1896 Sanriku earthquake, a magnitude of approximately 8.1. The shaking on land was moderate. Many people in the coastal villages felt it and went back to what they were doing. But the rupture was extremely shallow, right at the up-dip edge of the fault, and it moved a huge amount of water. The tsunami that arrived 30 minutes later was over 30 meters tall in places. It killed more than 22,000 people. It remains one of the deadliest tsunami disasters in Japanese history, and it happened along almost exactly the same segment of the trench we are discussing right now. Here is the unsettling implication. If today's earthquake was a relatively deep rupture, it may have released stress on the deep part of the fault interface. But the shallow part, the up-dip zone, the region closest to the seafloor, may not have ruptured at all. And that shallow segment is the one that produces tsunami earthquakes. That shallow segment is the one that killed 22,000 people in 1896. and that shallow segment, based on what we are seeing in the tsunami data, may have just been loaded further by today's event. A small tsunami now does not mean a small risk later. This is exactly the kind of situation the advisory is designed to address. A partial rupture, a stress transfer, a segment that moved, and a segment that did not. The science calls this incomplete rupture. Part of the fault slipped, part of the fault did not. And the parts that did not slip are now under more stress than they were before the rupture began. This is why the tsunami data, as reassuring as it might seem on the surface, is one of the pieces of evidence that has scientists most concerned tonight. Because to understand why an incomplete rupture on this particular segment is such a serious concern, you have to understand what happened 15 years ago on almost exactly this same stretch of coast. Part 4. The Shadow of 2011. On March 11, 2011, a magnitude 9.0 earthquake tore apart a 500-kilometre section of the Japan Trench. The shaking lasted 6 minutes. The tsunami that followed killed more than 15,000 people and triggered the Fukushima nuclear disaster. It was one of the largest earthquakes in recorded history, and it fundamentally reshaped how Japan and how the world thinks about seismic risk. But today's story is not about the 2011 earthquake itself. It is about what that earthquake left behind. Because when a subduction zone ruptures, it does not release stress uniformly across the entire margin. It releases stress in some places and transfers stress to others. This is a physical process called Coulomb stress transfer, and it is the key to understanding why today's event has scientists on edge. Here is how Coulomb stress transfer works, in the simplest possible terms. Imagine two ends of a giant sticky surface stuck together by friction. When one part of that surface suddenly slips, the parts immediately around it either get pulled along or get pushed against more tightly. Some neighbouring sections now have more stress on them than they did before, others have less. The overall effect is that a large rupture rearranges the stress field across a wide region, not just at the location of the rupture itself. Following 2011, multiple independent research teams ran detailed models of how stress had been redistributed across the Japan Trench. The 2011 rupture itself had released enormous stress across the central portion of the trench, the segment directly off Miyagi and Fukushima. But the segments to the north and south, the ones that did not rupture in 2011, actually had their stress increased. The Iwateoki segment, where today's earthquake occurred, was one of those segments, specifically identified in the published literature as stress-loaded, as ready, as waiting. Is what happened today the main event? Or is it the foreshock? Here is why that question cannot be separated from 2011. Because today's rupture was not an isolated event. It was, almost certainly, a delayed response to the stress redistribution that occurred 15 years ago. The models that predicted this segment would fail were published a decade ago. The fact that it has now failed is a confirmation of those models, but those same models also predict something else. They predict that if the Iwateoki segment fails only partially, the stress does not simply disappear. It migrates further, onto the next adjacent segment, or onto the shallow up-dip zone, or onto the deeper portion of the fault that is still locked. Delayed triggering is one of the most important concepts in modern subduction zone seismology. The idea that a large earthquake today can cause another large earthquake, not tomorrow, not next week, but years later, even decades later. The 2011 earthquake itself was preceded by a magnitude 7.3 foreshock only 2 days earlier, but the stress loading that made the main event possible had been accumulating for centuries, and the stress redistribution it caused is still propagating through the system today. This is why the advisory exists. This is why scientists are not sleeping tonight, because today's event, whatever else it is part of a chain reaction that began 15 years ago and has not yet resolved. The central question is whether what just happened is the end of that reaction, or the middle of it. Part 5. The Sanriku Gap Problem. To understand the specific stretch of fault we are discussing, you have to understand a concept in seismology called a seismic gap. A seismic gap is a section of a fault that has not ruptured in a long time, surrounded by sections that have ruptured more recently. Gaps matter because faults, over long timescales, tend to fill in their gaps. A region that has not had a large earthquake in 200 years is not a region that is safe. It is a region that is overdue. The Sanriku region, along the northern coast of Honshu, is one of the most studied and most complicated seismic gaps in the world, and today's earthquake happened directly inside it. Let me walk through the history. In 1896, the Sanriku tsunami earthquake struck offshore of this same stretch of coast. Magnitude approximately 8.1, shallow rupture, massive tsunami, more than 22,000 dead. In 1933, another earthquake struck, this one of magnitude 8.4, but of a different type. It was an outer rise event occurring seaward of the main trench in the subducting plate itself. It also produced a devastating tsunami. In 1994, a magnitude 7.7 earthquake occurred in roughly the same area, but this one was a partial rupture that did not produce a significant tsunami and did not release nearly as much stress as the earlier events. What you have across this stretch of the Sanriku coast is a pattern of incomplete stress release. Different earthquakes, on different parts of the fault system, each releasing some but not all of the accumulated energy. This is what seismologists call patchy failure. It is the opposite of the neat, clean, predictable rupture cycle you might imagine. Real faults do not fail in the same way every time. They fail in different patterns at different depths along different segments, depending on the specific stress state at the moment of failure. Is what happened today the main event, or is it the foreshock? Here is the problem with the Sanriku Gap. It is one of the least predictable sections of the entire Japan Trench. Because of this history of patchy failure, scientists cannot say with any confidence how today's rupture will affect the remaining stress in the region. One scenario is that today's earthquake released enough of the accumulated stress in this segment that the region will now enter a period of relative quiet. Another scenario is that today's earthquake released only the deepest, most stable portion of the locked zone, leaving the shallow segment more stressed than before. A third scenario is that today's earthquake is part of a multi-stage failure sequence, and that additional ruptures on adjacent or overlying patches are about to occur. All three scenarios are consistent with the available data. All three scenarios have historical precedent in this exact region, and nobody can tell you, right now, which scenario we are in. The gap does not just store stress. It hides how it will fail. That is the specific challenge this region poses to seismology. And that is why the advisory was issued with such unusual formality. Because in most fault systems, you can at least narrow the possible outcomes. In the Sanriku Gap, you cannot. The history of this region shows that anything from a full rupture to a slow creeping failure to a devastating tsunami earthquake is physically possible given the current stress state. And for the next 7 days, every one of those possibilities is on the table. The advisory is an acknowledgement that the science cannot eliminate any of them. Part 6. The geometry that matters. To understand why the tsunami was smaller than expected, and why that small tsunami is itself a piece of concerning evidence, you need to understand the geometry of a subduction zone fault. Subduction zones occur where one tectonic plate is being pushed underneath another. Along the Japan Trench, the Pacific plate is being forced down and westward, beneath the Okhotsk plate, at a rate of about 8 to 9 centimeters per year. The contact between the two plates is not a single line. It is a long, sloping surface, like a giant ramp descending from the seafloor down into the mantle. The shallow end of this ramp is near the seafloor itself, at the trench. The deep end is tens of kilometers below the surface, extending inland beneath Japan. Different parts of this ramp behave differently. The deep part, where temperature and pressure are high, tends to be the zone where strong shaking originates. Deep ruptures produce intense horizontal ground motion. The buildings sway, the ground trembles, the seismic waves radiate outward with tremendous energy. But because the rupture is deep, it does not lift the seafloor very much, so the tsunami it generates is relatively small. The shallow part, closer to the trench, behaves almost opposite. Shallow ruptures occur at low temperatures and low pressures, where the rock is weaker and can slide more slowly. The shaking from a shallow rupture is often surprisingly mild on land, because the seismic waves have to travel farther and through more heterogeneous rock to reach populated areas. But the seafloor above a shallow rupture can move dramatically, sometimes by 10 meters or more, and when 10 meters of seafloor move upward suddenly, they lift the entire water column above them. That water has to go somewhere. It goes outward, in all directions as a tsunami. Think of it this way. A deep rupture is like pulling a carpet out from under a table. The carpet slides, the table vibrates, but the water glass on top of the table barely moves. A shallow rupture is like peeling a sticker off a notebook and flinging the notebook upward. The notebook itself does not vibrate much, but the papers on top go flying. Today's rupture, based on the initial evidence, was a carpet-pulling event. Strong shaking on land, small tsunami, deep hypocenter, and that is why the tsunami came in at 80 centimeters instead of 3 meters. Is what happened today the main event, or is it the foreshock? Here is where the geometry becomes central, because if the deep part of the fault slipped today, but the shallow part did not, then the shallow part is now under more stress than it was before. The deep slip has transferred stress upward, toward the updip zone, toward the trench, toward the exact region that produces tsunami earthquakes like the one in 1896. We do not yet know the full slip distribution of today's rupture. Detailed slip models take days to produce because they require careful analysis of waveforms, GPS data, and seafloor deformation measurements. But the preliminary indicators all point toward a deep partial rupture. And a deep partial rupture in this segment is precisely the scenario that most concerns the scientists watching this system right now, because it is exactly the kind of event that can set up, rather than release, the next catastrophic failure, which is why the next 7 days are critical. Part 7. What 1% actually means. Let's talk about the number, 1%. That is the probability, as communicated by the Japan Meteorological Agency, that a magnitude 8 or larger earthquake will occur in this region within the next 7 days. 1% sounds small, 1% sounds manageable, 1% sounds, for most people, like something you do not need to worry about. That is the wrong way to read this number. Human beings are very bad at reasoning about rare events. Our intuition about probability is shaped by the kinds of events we encounter in daily life, things with frequencies in the tens of percent. A 50% chance of rain, a 20% chance of a flight being delayed. When we see a 1% probability, our instinct is to round it to 0. And for most everyday decisions, that is fine. But earthquakes are not everyday events. Earthquakes, especially large subduction earthquakes, are rare in the strict statistical sense. The baseline probability of a magnitude 8 in this region, in any given 7-day window, is approximately 1/10 of 1%. 1 in 1,000. That is what the system looks like on a normal week. Today's advisory is saying that the probability has increased to approximately 1%, 1 in 100. That is a 10-fold increase. And in any rare event system, a 10-fold increase is a radical shift. Consider how we treat 10-fold increases in other contexts. If the background probability of a nuclear plant accident on a given day is 1 in a million, and that probability jumps to 1 in 100,000, regulators do not respond by saying, well, it is still very unlikely. They respond by shutting down the plant. If the probability of a structural failure in a bridge increases by a factor of 10, engineers do not issue reassurances. They close the bridge. The absolute number is still small, but the relative change communicates that the system has entered a different state. It is not behaving the way it normally does, and in rare event systems, the tail is where the catastrophes live. Is what happened today the main event, or is it the foreshock? Here is the connection. A 1% probability of a magnitude 8 or larger within 7 days is not a prediction that such an earthquake will occur. It is a statement that the system is temporarily unstable. Earthquakes, it turns out, are not evenly distributed in time. They cluster. After a large earthquake, the probability of another large earthquake in the same region is significantly elevated, specifically in the days immediately following. This is not controversial. It is one of the most robust empirical findings in seismology. It is the basis for the entire concept of aftershock sequences. What the advisory is doing is applying this clustering behavior to the specific case of subduction zone megaquakes. Most aftershocks are smaller than the main shock, but a small percentage of them are larger. And when they are larger, the original earthquake gets reclassified retroactively as a foreshock. The 7-day window matters because that is when the clustering effect is most concentrated. Within the first week after a large earthquake, the probability of a follow-up event is at its peak. After 7 days, the probability decays rapidly back toward baseline. It does not return to baseline entirely, but the acute phase of elevated risk passes. So when the JMA says 1% over 7 days, What they are really saying is that the next 7 days represent a temporary window during which the system is 10 times more unstable than usual. Most of the time, nothing will happen. But when something does happen, it often happens now, in the hours and days immediately after the initial event, and that is the nature of the specific risk the advisory is designed to communicate. The honest assessment is this: if you live in one of the 182 municipalities covered by the advisory, your personal probability of being affected by a magnitude 8 earthquake over the next week has gone from negligible to small. It has not gone from negligible to high, but it has changed, and that change is significant enough that the Japanese government, an institution not known for issuing hysterical warnings, has felt the need to tell you about it in the most formal language available to it. The question of what to do with that information is harder than the question of what it means. Part 8. Foreshock Logic. Here is one of the strangest and most unsettling facts in all of seismology. A foreshock is not a category of earthquake that can be identified while it is happening. It is a classification that can only be applied retroactively after a larger earthquake follows it. Until that larger earthquake occurs, what you have is just an earthquake. It only becomes a foreshock when something bigger comes along to redefine it. This sounds like a technicality. It is not. It is the single most important limitation on the predictive power of seismology. Because if you cannot identify a foreshock in real time, then every large earthquake that occurs has to be treated, at least provisionally, as a possible foreshock. Most of them will not turn out to be foreshocks, but some of them will, and the science has no reliable way to sort them in advance. Here are the statistics. Across the global historical record of large earthquakes, somewhere between 15 and 20% of magnitude 7 or larger events are preceded by clear foreshock sequences. The other 80 to 85% occur without obvious warning. When foreshocks do occur, they are sometimes minutes before the main shock, sometimes hours, sometimes days, sometimes weeks. There is no consistent pattern, no reliable timescale, no clear signature that distinguishes a foreshock, while it is happening, from a regular earthquake that will not be followed by anything bigger. The 2011 Tōhoku earthquake is the most relevant example. On March 9th, 2011, a magnitude 7.3 earthquake occurred off the coast of Miyagi. Significant, damaging, worthy of attention. At the time, it was treated as a moderately large earthquake. There were some discussions in the seismological community about whether it might be a foreshock to something larger, but those discussions were speculative. The probability that a magnitude 7.3 is a foreshock to a magnitude 9 statistically is small, less than 1%. 2 days later, on March 11th, the magnitude 9.0 main shock occurred, and the magnitude 7.3 from 2 days earlier was immediately retroactively reclassified as a foreshock. It had always been a foreshock, but that label only became correct after the main shock happened. Is what happened today the main event, or is it the foreshock? Here is why that question has such weight tonight. Because today's earthquake is a magnitude 7.7, that is already larger than the 2011 foreshock. If it were part of a similar sequence, the main shock it preceded would have to be even larger than the 2011 main shock, a magnitude 9.2 or 9.3 or larger. Those are numbers that do not fit on ordinary risk charts. Those are numbers that redefine what catastrophe looks like. Now, to be absolutely clear, the statistical probability that today's earthquake is a foreshock to something of that scale is still low. Most magnitude 7.7 earthquakes are not followed by anything bigger. They are themselves the main event. They release stress, the aftershock sequence decays, the region enters a period of relative quiet. That is the most common outcome. That is probably what will happen here, but probably is not the same as certainly, and the specific context of today's event, the stress loading from 2011, the prior activity on this segment, the partial rupture suggested by the tsunami data, all of these factors push the probability of a foreshock scenario above the global baseline, not to 50%, not to 10%, but above the typical 1 to 2% range that would apply to an average magnitude 7.7 somewhere in the world. And when you multiply those shifted probabilities by the potential consequences of being wrong, the expected cost is enormous. That is why the advisory exists. We may already be inside the foreshock. That is not a statement of probability. It is a statement of epistemic honesty. We cannot rule it out. The tools of seismology do not let us rule it out, and the advisory is the formal institutional acknowledgement of exactly that uncertainty. which brings us to the pattern of aftershocks we have seen so far, and what that pattern does and does not tell us about what might be coming. Part 9. Aftershock Pattern Anomaly. In the hours since the main event, the Japan Trench region has produced an aftershock sequence that is, in most respects, unremarkable. About 15 aftershocks of magnitude 4.5 or larger. The largest so far has been a magnitude 6.1. Nothing catastrophic. Nothing that would ordinarily attract special attention. Just the standard tapering of seismic energy that follows a large rupture. But there is a rule in seismology called Barth's law. It is a simple empirical observation about earthquake sequences. On average, the largest aftershock of a sequence is approximately 1.2 magnitude units smaller than the main shock. It is a statistical regularity, not a strict law, but it holds up across a huge range of fault systems and earthquake types. A main shock of magnitude 7.7 under Barth's law should produce a largest aftershock of approximately magnitude 6.5. So far, the largest aftershock we have seen is magnitude 6.1. That is below the expected value, not dramatically below, but noticeably below. The magnitude gap between the main shock and the largest observed aftershock is larger than typical, about 1.6 units compared to the expected 1.2. What does that mean? Here is where the interpretation becomes difficult. One reading is that this is simply a normal decay pattern, still in its early phase, and that a larger aftershock may yet occur. Barth's law is a statistical average, not a deterministic rule. Many individual sequences deviate from it by a significant margin. It is entirely possible that over the next several days, a magnitude 6.3 or 6.5 aftershock will occur, bringing the sequence back into line with expectations. Another reading, more unsettling, is that the sequence has not yet produced its largest member, that the stress released by today's event was incomplete, that the remaining stress in the region is still accumulating toward another release, and that the apparent deficit in aftershock magnitude is a signal, not a coincidence. Is what happened today the main event, or is it the foreshock? The aftershock data by itself cannot answer that question. It is consistent with both scenarios. A sequence that is still decaying normally will eventually produce a 6.5 or so aftershock and then taper off. A sequence that is building toward a larger event will also produce intermediate aftershocks, but will additionally produce at some point an earthquake that is larger than the original. And right now, we cannot tell from the aftershock pattern alone which of those sequences we are in. This is one of the fundamental frustrations of modern seismology. The data does not resolve the scenarios fast enough. We can monitor, we can analyze, we can run models, but we cannot, in the crucial window when decisions have to be made, tell you whether what you are seeing is a normal decay or an incomplete release. And in this specific case, with this specific fault, with the specific history of stress loading from 2011, the difference between those two scenarios is the difference between a news cycle and a catastrophe. Even the aftershock pattern cannot yet confirm whether this event relieved stress or is leading into something larger, which is why the attention shifts necessarily to the scenarios that would follow if the sequence is still evolving, and the first and most worrying of those scenarios is the one we hinted at earlier: the tsunami earthquake. Part 10. The tsunami earthquake scenario. A tsunami earthquake, in the strict technical sense, is an earthquake that produces a tsunami significantly larger than its magnitude would suggest. These events were first recognized in the 1970s by the seismologist Hiru Kanamori, who noticed that certain earthquakes seem to generate anomalously large ocean waves, despite producing relatively moderate ground shaking. The defining characteristic of a tsunami earthquake is not its total energy release. It is the specific way that energy is distributed, both in space and in time. A tsunami earthquake occurs when a rupture happens very close to the trench, in the shallowest part of the subduction interface, and ruptures slowly. Slow rupture means the seismic waves that travel through the crust are of long wavelength and low frequency. These waves do not shake buildings very much. They do not feel violent to people on land. Often, residents in coastal areas feel only a gentle, prolonged swaying. Some people do not feel the earthquake at all, but the seafloor directly above the rupture moves a lot. And because the rupture is shallow, there is very little rock above it to absorb that motion. The water, millions of tons of it, gets lifted up, sometimes 10 meters, sometimes 20, and then it spreads outward, driven by gravity, as a tsunami. The 1896 Sanriku tsunami earthquake is the archetype of this phenomenon. The magnitude was approximately 8.1. Shaking along the coast was, by most accounts, mild to moderate. People felt it, recognized it as an earthquake, but did not evacuate in large numbers. Many went back to their homes or their fishing boats. 30 to 40 minutes later, the tsunami arrived. The waves were in some places 38 meters tall. Entire villages were erased from the coastline. The death toll was over 22,000. And the earthquake had given almost no warning. Is what happened today the main event? Or is it the foreshock? Here is the specific version of the foreshock question that the tsunami earthquake scenario raises. If today's rupture occurred in the deep, frictionally locked part of the subduction interface, and if it did not rupture the shallow up-dip zone, then the shallow up-dip zone is now under increased stress. The Coulomb stress transfer from today's deep slip would have loaded the shallow segment further. And that shallow segment is exactly the kind of fault geometry that produces tsunami earthquakes. This is not a prediction, it is a scenario. The scientific community does not have tools to tell you how likely this specific scenario is relative to other possible outcomes. But it is a scenario that is consistent with the evidence. It has historical precedent in this exact region, and it is one of the reasons the advisory was issued in such formal language. A shallow up-dip rupture in the Sanriku segment would not necessarily be felt strongly on land. The first warning most people might receive would be the JMA tsunami alert itself, and because tsunami earthquakes have slower rupture durations than regular earthquakes, the early warning systems that rely on detecting the initial P waves may produce less accurate magnitude estimates in the critical first minutes. The warning might come late, or it might underestimate the size of the wave. These are exactly the conditions under which the deadliest tsunami disasters occur. Not when the earthquake is large and obvious and forces everyone to evacuate, but when the earthquake is deceptively mild and the population stays put and the wave arrives without enough warning to move. This is the worst case scenario on the table right now. It is not the most likely scenario. The most likely scenario, by a significant margin, is that today's event was a complete or near complete rupture. The aftershock sequence will decay normally and the region will return to background seismicity over the coming weeks. But the worst case scenario cannot be ruled out. And it is the possibility of the worst case scenario that is keeping the advisory in place for the next 7 days. Which brings us to the question of what happens next on the fault itself. Not in terms of discrete earthquakes, but in terms of the slow, continuous processes that follow every major rupture. Those processes, over the next 72 hours, may determine which scenario we are actually in. Part 11. Afterslip, barrier or trigger. When a subduction zone earthquake occurs, the rupture itself lasts anywhere from seconds to a few minutes, but the deformation of the crust does not stop when the shaking stops. For days, weeks, and even years after a major rupture, the fault continues to move slowly. This slow, continuous motion is called afterslip, and afterslip is one of the key processes that scientists monitor to understand what is really happening on a fault after a major event. Afterslip can happen in two places. Roughly speaking, it can happen on the same segment that ruptured, essentially a slow continuation of the main rupture, as the fault finishes releasing its stored stress. Or it can happen on adjacent segments, as those segments respond to the stress transfer from the main event. The first kind of afterslip is stabilizing. It means the system is finishing its release and settling into a quieter state. The second kind is destabilizing. It means stress is migrating to new parts of the fault, increasing the likelihood of further earthquakes. Telling these two kinds apart is one of the most important things scientists do in the days after a large subduction earthquake. They do it primarily with GPS data. Japan has an extraordinarily dense network of GPS stations called GeoNet that can measure ground motion to within a few millimeters. When the ground starts moving in a particular direction at a particular site, that motion reveals which parts of the fault are slipping and which are not. Is what happened today the main event, or is it the foreshock? Afterslip behavior may be the single most important piece of evidence for answering that question over the next 72 hours. If the GPS data over the coming days shows afterslip concentrated on the deep portion of the fault interface, continuing the motion of today's rupture, that is a reassuring signal. It suggests the system is releasing stress and will decay toward quiescence, If, instead, the GPS data shows motion migrating upward toward the shallow updip zone or laterally toward adjacent segments, that is a much more concerning signal. It suggests stress is not being released, it is being redistributed, and the system may be setting up a second rupture rather than finishing the first. The first 72 hours are critical. After that, the signals become muddier as ongoing afterslip, aftershocks, and background tectonic motion become harder to distinguish. But in the first 72 hours, the direction and magnitude of afterslip is often clear enough to make preliminary interpretations, and those interpretations will inform in a very concrete way whether the advisory is extended beyond its initial 7-day window or allowed to expire. Scientists in Japan are, right now, staring at GPS time series, looking at millimetre-scale motions of stations along the coast, trying to read, in those tiny displacements, the answer to a question that affects the lives of tens of millions of people. Afterslip behaviour may decide whether the system stabilises or escalates into a larger rupture. That is the scale of what is being measured right now. But the potential for cascade does not stop at the edges of the Iwate-oki segment. There are other systems connected to this one, other faults that could, in principle, be influenced by today's event. And while those influences are more speculative, they are worth briefly mentioning. Part 12. Cascading Fault Interaction. The Japan Trench does not exist in isolation. To the north, it connects to the Kuril Trench, which runs along the Kuril Island arc up toward the Kamchatka Peninsula. To the east, at a much greater distance, it connects through the Pacific Plate Subduction System to the Aleutian Trench along the southern edge of Alaska. These are all parts of the larger Pacific Ring of Fire, a network of subduction zones that wraps around the ocean and produces the vast majority of the world's largest earthquakes. The question of whether a major earthquake on one segment of this network can influence distant segments has been studied for decades. The general answer is that direct stress transfer effects decay rapidly with distance. Coulomb stress changes from a magnitude 7.7 earthquake are negligible at distances of more than a few hundred kilometers, so the likelihood that today's rupture will directly trigger a major earthquake on the Kuril Arc, or the Aleutians, or any other distant subduction zone is very low. However, there is a more subtle form of interaction that researchers have documented. It is called dynamic triggering, and it involves the passing seismic waves from a large earthquake temporarily stressing fault systems far from the epicenter. Dynamic triggering has been observed after some of the largest earthquakes in recent history, producing small seismic responses on faults thousands of kilometers away. These responses are usually minor, but they are real. Is what happened today the main event? Or is it the foreshock? Even distant interactions matter only insofar as they influence whether this sequence escalates. The more realistic concern is not that today's earthquake will trigger something on the Aleutians. It is that the broader pattern of activity on the Japan Trench, of which today is only the latest chapter, reflects a long-term evolution of the entire northwestern Pacific subduction system. And that long-term evolution is not predictable on the timescales we're considering tonight. This is a passing concern, not a central one. The seismological community is watching for anomalous signals on nearby and distant fault systems as a matter of standard protocol after any major event. But the focus, tonight, and for the next 7 days, is squarely on the Japan Trench itself, and on the specific segments immediately adjacent to today's rupture. Those are the segments that matter most. Those are the segments where the next rupture, if there is one, is most likely to occur. Which brings us back to the central anomaly of today's event, the thing that makes it so difficult to interpret: the absence of any clear warning signal in the hours before it happened. Part 13. No foreshock, no warning. In the 72 hours before today's magnitude 7.7 rupture, there were no significant earthquakes in the Iwate-oki segment, no foreshock swarm, no anomalous seismic activity, no observable buildup of any kind. The seismic network that blankets this region, one of the densest and most sophisticated monitoring arrays on the planet, capable of detecting earthquakes too small for any human to feel, recorded nothing unusual. The GPS stations that measure ground deformation to millimetre precision showed no anomalous motion. The ocean bottom pressure sensors that sit on the seafloor directly above the fault showed no unusual signals. Every instrument pointed at this segment of the Japan Trench in the 72 hours before the rupture said the same thing. Quiet, normal, unremarkable. And then, at 4:53 in the afternoon, the fault moved 7.7. No siren, no warning, no gradual escalation that gave anyone a moment to prepare mentally for what was coming. Just the rupture itself, arriving out of apparent stillness, and then everything that followed. The shaking, the tsunami warnings, the evacuation orders, the megaquake advisory, all of it cascading outward from a single event that the most advanced monitoring system in the world did not see coming. I want to sit with that for a moment, because I think it is the piece of tonight's story that is hardest to fully absorb. We live in an era of extraordinary scientific instrumentation. We have seismometers that can detect the passage of seismic waves from earthquakes on the other side of the planet. We have GPS networks that measure the slow creep of tectonic plates in real time. We have satellite radar systems that can detect centimetre-scale deformation of the Earth's surface from orbit. We have ocean bottom observatories sitting directly on top of the most dangerous fault systems on Earth. And none of it, not one instrument, not one data stream, not one monitoring system, gave any indication that this fault was about to rupture. The silence was total, and then the silence ended. This is unfortunately not an anomaly, it is the norm. About 80 to 85% of large subduction earthquakes occur without any clear precursors. No foreshock sequence in the hours or days before the main event. No detectable change in background seismicity rates. No anomalous surface deformation that rises above the noise floor of the instruments. The fault accumulates stress over decades or centuries, reaches its failure threshold and slips. The transition from stable to unstable happens at scales of time and space that our instruments, for all their sophistication, cannot yet resolve. The fault simply fails, and the first indication that anything has happened is the earthquake itself. Seismologists have been searching for reliable precursors for as long as seismology has existed as a science. The search has been serious, well-funded, and genuinely motivated by the understanding that a reliable precursor detection system could save hundreds of thousands of lives. Researchers have monitored groundwater levels in wells near active fault zones, looking for the pressure changes that might signal an impending rupture. They have measured radon concentrations in soil and water, because radon, a radioactive gas that seeps through rock fractures, sometimes shows anomalous behavior before earthquakes. They have tracked electromagnetic signals, looking for the electrical and magnetic anomalies that some theories predict should accompany the buildup of stress in crystalline rock. They have studied animal behavior, cataloguing the reports of unusual activity in the hours before major earthquakes, dogs refusing to enter buildings, fish behaving strangely, birds abandoning roosts, trying to determine whether animals are detecting something our instruments are not. They have analysed changes in the statistical patterns of small earthquakes, looking for the subtle shifts in seismicity rates that might indicate a fault approaching failure. Some of these signals have shown correlations with specific events, in hindsight. After the fact, researchers have sometimes been able to identify anomalies in the data that preceded a major earthquake. Anomalies that were present in the record but not recognised as significant until the earthquake provided context. The radon spike that occurred before a major Italian earthquake. The groundwater level change recorded near a fault in California weeks before it ruptured. The electromagnetic anomaly detected before a significant Japanese event. These correlations exist. They have been published. They have been studied. And none of them, not one, across decades of research and thousands of events, has produced a reliable operational prediction system. A system that can say, before the earthquake, that this specific fault will rupture within this specific time window at this specific magnitude, with enough reliability to justify the social and economic cost of acting on the warning. The fundamental problem is not instrumentation, it is physics. Earthquakes, especially large earthquakes, are nonlinear events. They do not scale predictably from small precursors to large outcomes. They depend with extreme sensitivity on the exact state of the fault, at the exact moment of failure, the distribution of stress across the fault plane, the pore fluid pressure in the fault zone, the frictional properties of the contact surface, the geometry of asperities and barriers that control how a rupture initiates and propagates, and the state of the fault cannot be measured directly. It is 30 kilometers below the seafloor. It is inaccessible. It can only be inferred from indirect observations at the surface, most of which have poor spatial resolution and significant time lags. We are trying to read the internal state of a system we cannot see, using instruments that are separated from it by kilometers of rock and water, looking for signals that may or may not exist, on timescales that may or may not be relevant. It is in some ways the hardest measurement problem in all of Earth science. Is what happened today the main event, or is it the foreshock? The absence of precursors before today's rupture is itself a piece of evidence in that question, and it is not a reassuring one. Here is why. There are, broadly speaking, two ways a fault can fail. The first is a slow, progressive failure, where stress builds gradually to the rupture threshold. The fault begins to creep slightly as it approaches failure. Small earthquakes initiate and propagate in the fault zone, and the system gives observable signals of its approach to the breaking point. This kind of failure tends to produce foreshock sequences. It tends to produce the anomalous precursory signals that researchers look for. It tends to be, in retrospect, readable. The second is an abrupt, stress-driven failure, where the fault is held in a locked state by high frictional resistance right up to the moment it crosses the failure threshold and then releases catastrophically without any precursory phase. No gradual creep, no foreshock swarm, no warning signals of any kind. Just the sudden transition from locked to ruptured. Today's rupture was the second kind. The instruments confirm it, 72 hours of quiet and then a 7.7. That pattern is consistent with a fault that was under high stress and high frictional resistance, locked tightly against the opposing plate, accumulating elastic strain silently until it reached the exact threshold at which that resistance could no longer hold. And abrupt, stress-driven failures of that kind, the ones that do not give the system time to produce detectable precursors, are, in general, more likely to be part of ongoing stress redistribution than to represent the final, complete release of a long-term accumulation. A fault that fails gradually tends to release its stress completely as it fails. A fault that fails abruptly tends to release its stress incompletely, leaving residual stress available for subsequent events. The system crossed the threshold silently. That is not a dramatic flourish. It is a literal description of the physics. The Iwateoki segment moved from stable to unstable without passing through any intermediate state that our instruments could detect. And the concern among the scientists monitoring this region tonight is not abstract, it is specific. Because if this segment crossed its threshold silently, the adjacent segments could do the same. The shallow up-dip zone, which may not have ruptured today, which sits above the deep portion of the fault that did rupture, which is now under increased stress from today's Coulomb stress transfer, that zone could be approaching its own threshold right now. The GPS stations would not necessarily show it. The seismic network would not necessarily show it. The ocean bottom sensors might show it, if the signal were large enough, but only after the fact, after the rupture had already initiated. The silence that preceded today's earthquake is not a one-time feature of this segment. It is a property of this class of fault failure, and it applies equally to every adjacent segment that is now sitting in an elevated stress state because of what happened today. This is why the advisory exists. Not because the JMA has some secret knowledge that another earthquake is imminent, not because the models have identified a specific signal that points to a specific outcome, but precisely because they have not. The advisory is an acknowledgement, formal and institutional, that the tools of seismology cannot tell us what is about to happen. They can tell us that the system is in an elevated state. They can tell us that the probability of further major events has increased. They can tell us that the coming week is a period of heightened vigilance. What they cannot tell us is whether the next threshold crossing will happen tomorrow, or next week, or next year, or not at all. And they cannot tell us whether it will be silent like today's was, or whether it will announce itself with foreshocks that give the population time to move. That is the truth the advisory communicates. That is the reason it exists, not as a prediction, not as a reassurance, as an honest statement of what the science knows and what it does not. As an acknowledgement that the silence before today's earthquake was not evidence of safety. It was evidence of a fault that does not warn you, and that fault is still there. The adjacent segments are still there, the stress is still there, and the instruments that failed to see today's rupture coming are the same instruments that are watching for the next one, watching carefully, watching honestly, and watching, it must be said, with the full knowledge that they might not see it until it is already too late. Part 14. The limits of prediction. When people hear that a government agency has issued a warning about elevated earthquake risk, The natural reaction is to assume that the agency knows something specifically, that they have some kind of insider data that tells them an earthquake is coming, and they are warning the public. That is a prediction. And prediction, in the strict sense, is not what seismology does. Here is the distinction. A prediction is a specific statement that a particular event will occur at a particular time and place. It has an expiration. It can be right or wrong. Predictions of earthquakes with any useful specificity are not currently possible. Despite decades of research, no one can tell you that an earthquake of a particular magnitude will occur at a particular location on a particular day. The science does not support that kind of claim. A probability estimate, by contrast, is a statistical statement about the likelihood of events over a range of possible outcomes. It does not say that anything will happen. It says that, given the current state of the system, the distribution of possible outcomes has shifted in a particular way. The 1% probability in the advisory is a probability estimate, not a prediction. It does not assert that a magnitude 8 will occur in the next 7 days. It asserts that the probability has increased tenfold from baseline. Why does this distinction matter? Because it affects how the advisory should be interpreted. If you read the advisory as a prediction, you will probably either panic, expecting the earthquake to come, or dismiss it when the earthquake does not come, thinking the agency was crying wolf. Both reactions are wrong. The advisory is neither a prediction nor a false alarm. It is an honest statement about a specific statistical condition that exists right now, for a limited time, in a specific region. Modern seismology operates almost entirely in the probability mode. The best researchers in the field use ensemble-based models, which combine multiple scenarios and physical constraints to produce forecasts of earthquake occurrence over time windows ranging from hours to centuries. These models are not precise. They produce broad ranges of possible outcomes, with estimated probabilities attached to each. They are useful for long-term planning, for building codes, for insurance pricing, for risk management. They are not useful for telling you, personally, whether to evacuate your house on any particular afternoon. Is what happened today the main event? Or is it the foreshock? The advisory reflects uncertainty, not foresight about what comes next. That is the honest framing. The seismological community has looked at the data, has run the models, has applied the best available physics, and has concluded that the state of the system has shifted into a range where further major events are more likely than usual. They cannot tell you whether such events will occur. They can only tell you that the probability is elevated, and they have chosen to tell you, rather than keeping that information internal, because they believe the public deserves to know. That belief that the public deserves to know even when the science cannot offer certainty is the cultural and institutional foundation on which the entire advisory system rests, and it is worth understanding how that foundation came to exist. Part 15. Why the advisory exists. Before 2011, Japan did not have a formal advisory protocol for elevated earthquake risk following a major event. Think about what that actually means. One of the most seismically active nations on Earth, a country that has been building earthquake-resistant infrastructure for generations, a country whose entire coastal culture is shaped by the memory of tsunamis, and it had no formal system for telling its people that a large earthquake might be followed by an even larger one. The institutional response to large earthquakes was focused entirely on the immediate aftermath: search and rescue, tsunami evacuation, infrastructure assessment. The question of whether another major earthquake might follow within days or weeks was not addressed through formal public communication. It was considered a matter for internal scientific discussion. A conversation between researchers and agency analysts conducted in technical language, in conference rooms and monitoring centres, away from the public entirely. The assumption, whether stated or not, was that the public could not be trusted with probabilistic uncertainty. That telling people the risk had increased, without being able to say by how much or when or where exactly, would cause more harm than good. Panic, false alarms, disruption. That was the calculation. And for decades it held. 2011 changed that calculation permanently. The sequence of events that preceded the magnitude 9.0 main shock, including the magnitude 7.34 shock that struck just 2 days earlier, became the central case study in what happens when elevated risk is not communicated. That foreshock, a significant earthquake in its own right, was processed by the scientific community as a notable event. There were quiet discussions about whether it might signal something larger. Those discussions stayed quiet, they stayed internal, and 2 days later, the magnitude 9 arrived, and 15,000 people died, and the Fukushima reactors failed, and the entire northeastern coastline of Japan was rewritten. In the aftermath, the question that haunted the scientific and governmental community was not just what they had failed to predict, it was what they had failed to say, what they had known, or suspected, or considered possible, and chosen not to communicate because the uncertainty felt too large to put into public language. The post-event analysis took years. It was careful, methodical, and ultimately honest in a way that institutional reviews rarely are. The conclusion, reached through extensive deliberation, was straightforward but profound. The Japanese public had a right to know about elevated risk, even when the science could not provide certainty. The value of the information was judged to be greater than the cost of potential false alarms. Not because false alarms are costless, they are not. Unnecessary evacuations disrupt lives, damage economies, erode public trust. The Japanese government understood all of that, and it decided, after looking at the bodies and the rubble and the contaminated groundwater and the families that no longer existed, that the cost of under-preparation was categorically larger than the cost of overwarning. That is not an obvious conclusion. It is a hard-won one. And it produced a system that did not exist anywhere in the world before Japan built it. The Megaquake Subsequent Quake Advisory System was formally established in 2022. It was designed specifically for the Nankai Trough, the subduction zone running along the southwestern coast of Japan that is believed to be capable of producing megathrust earthquakes of magnitude 9 or larger, potentially affecting tens of millions of people across the most densely populated corridor in the country. The Nankai Trough sits beneath the waters off Shizuoka, Aichi, Mie, and Kochi. It is, by most assessments, the single most dangerous fault system in Japan that has not ruptured in living memory. The advisory protocol was built for that fault first, and later extended to cover other subduction zones around Japan, including the Japan Trench region, the one running along the northeastern coast, the one that produced 2011, the one that moved tonight. The criteria for issuing an advisory are specific and deliberately restrictive. Not every large earthquake triggers one. The protocol is not designed to activate every time the ground shakes hard somewhere in Japan, because if it were, it would activate constantly, and the public would stop taking it seriously within a year. The advisory is reserved for events that meet particular thresholds of magnitude, of location relative to known fault geometry, and of stress transfer potential, meaning the rupture has to occur in a place and in a way that meaningfully increases the probability of a follow-up event on an adjacent or overlapping fault segment. The bar is high. The scientific judgment required to clear it is not trivial. And since the system was created in 2022, that bar has been cleared exactly 3 times. Tonight makes the 3rd. Pause on that number for a moment because it matters more than it might seem. 3 times in 3 years. On a fault system that produces thousands of earthquakes every year, 3 times that the collective judgment of Japan's most senior seismologists has been that the threshold was met, the risk was real, and the public needed to know. That is not a system crying wolf. That is a system exercising extraordinary restraint and then speaking very clearly when it finally speaks. Is what happened today the main event? Or is it the foreshock? The advisory does not answer that question. It is not designed to. And this is the part that I think most news coverage gets wrong, because most news coverage is built around resolution, around answers, around the clean narrative where the expert tells you what happened and what it means and what comes next. The advisory is the opposite of that. It is designed specifically and intentionally to acknowledge that the question cannot be answered, and that the public should be aware of the elevated risk that comes with not being able to answer it. It is a document that says, in the most formal institutional language available, we do not know, and you deserve to know that we do not know. That is a remarkable thing for a government agency to say. Agencies do not typically lead with uncertainty. They lead with reassurance, with control, with the message that competent people are handling the situation and the public should remain calm. The Mega Quake Advisory is the explicit rejection of that instinct. It is a formal admission by one of the most competent and well-resourced earthquake monitoring agencies in the world that the science has limits, that the models cannot see through to the outcome. that the next 7 days are a period of genuine uncertainty, and that uncertainty itself is a reason to be vigilant. Let me say that one more time because I want it to land properly. The advisory is not reassurance. It is the opposite of reassurance. It is a warning issued in the most carefully calibrated language the JMA can produce, that the system has moved into a different regime. That the normal week, the background hum of low-level seismic risk that defines life along this coastline is temporarily over. That for the next 7 days, the probability distribution of possible outcomes has shifted in a direction that everyone monitoring this fault would prefer it had not shifted, and the question of what that regime will produce, whether it decays quietly back to baseline, or whether it escalates towards something that redefines catastrophe for an entire generation, remains completely open. Now here is where I want to be precise about something, because I think it is genuinely important for how you process this information. The advisory is not the JMA predicting that a megaquake is coming. Earthquake prediction, in the strict sense, is not something seismology can currently do. No agency on Earth can tell you that a specific earthquake of a specific magnitude will occur at a specific location on a specific date. The science does not support that claim. What the advisory represents is a probability shift, a formal statement that the distribution of possible outcomes over the next 7 days now includes catastrophic scenarios at a frequency 10 times higher than normal. 1% versus 1/10 of 1%. That sounds like a small number. But in a rare event system, where the tail end of the distribution is where civilizations are reshaped, a tenfold increase is not a rounding error. It is a different world. Which brings us necessarily to the question of how this story is being received outside the strict seismological community. Because earthquakes do not happen in a vacuum. They happen in a public space full of anxieties and narratives and fears, shaped by memory and media and the very human tendency to pattern match our darkest experiences onto the present moment. And in that public space, the gap between what the science actually says and what people hear the science saying can become very quickly enormous. Understanding that gap and what fills it when official communication runs out is the next piece of this story, and it is one that the data alone cannot tell you. Part 16. Fukushima, Fear and Framing. The epicenter of today's earthquake was approximately 250 kilometers north of the Fukushima Daiichi nuclear site. 250 kilometers. To put that in perspective, that is roughly the distance between London and Manchester, or between New York City and Boston. It is not next door. But in geologic terms, in the language of fault systems and stress fields and subduction zones that span hundreds of kilometers, it is close enough to be in the same general region, close enough that the shaking reached the plant, close enough that every monitoring system on the site activated simultaneously, and close enough that within minutes of the rupture, before most of the world even knew an earthquake had occurred, a specific set of people at a specific set of control panels were already running through checklists that exist for exactly this scenario. The shaking at the Fukushima site was measurable but moderate. The instruments recorded it. The automated systems responded to it. And then, as the shaking subsided, the assessments began. No damage has been reported to the containment structures. No damage to the storage facilities, where hundreds of thousands of tons of treated and partially treated water are held in tank farms that stretch across the site like a small industrial city. No anomalies in the ongoing decommissioning work, the slow, extraordinarily complex process of dismantling 3 melted reactor cores that has been underway for 15 years and will continue for decades more. The Tokyo Electric Power Company confirmed, in its preliminary assessments released within hours of the event, that all critical systems are functioning normally. The plant is stable. That is the official position, and based on the available evidence tonight, it is accurate. But here is the thing about Fukushima. The word itself has become something more than a place name. 15 years after the 2011 disaster, it functions in public discourse as a kind of shorthand, a symbol, a single word that carries within it the entire weight of the worst nuclear accident since Chernobyl. The image of the hydrogen explosions, the exclusion zone, the fishing communities whose livelihoods were destroyed not by the tsunami itself but by the contamination that followed, the hundreds of thousands of people who were evacuated and in many cases never returned. The ongoing debate about water releases into the Pacific. All of that is compressed into one word, and any major earthquake off the coast of Japan, on this coast, in this region, will cause that word to surface immediately. In social media posts, in news headlines, in the minds of people who lived through 2011 or watched it unfold from the other side of the world and never quite forgot what they saw. That reaction is understandable. It is not irrational. It is in fact the entirely reasonable response of people who have learned, the hard way, that the gap between stable and catastrophic at a nuclear facility can close faster than anyone expects. In 2011, the reactors at Fukushima Daiichi were operating within normal parameters right up until the tsunami overtopped the seawalls and knocked out the backup power systems. The transition from normal to crisis took hours. The full scale of the disaster took days to become clear, and the lesson that many people took from that sequence was not a technical one about backup generator placement or seawall design specifications. It was a simpler and more visceral lesson. Things that are described as stable can become unstable very quickly when the ground starts moving. So when people hear tonight that Fukushima is stable, the honest thing to acknowledge is that their skepticism is not unfounded. It is earned. And the appropriate response is not to dismiss it, but to be precise about what stable actually means in this context and what conditions would change that assessment. Right now, stable means this. The containment structures are intact. The fuel removal operations, which have been proceeding slowly and carefully through the damaged reactor buildings, have been paused as a precautionary measure, but have not been compromised. The treated water storage tanks, which represent one of the most physically vulnerable aspects of the ongoing decommissioning, showed no structural damage in the post-earthquake inspection. Radiation monitoring stations around the site perimeter are showing normal readings. The ocean monitoring network, which tracks radiological conditions in the waters off the Fukushima coast, has not detected any anomalies. By every available measure, the site is in the same condition tonight that it was in this morning. The earthquake changed the seismic risk profile of the region. It did not change the physical status of the plant. But, and this is the part that matters for the next 7 days, concern about Fukushima does not rest on what happened today. It rests on what might happen next. Because the advisory that is now active over this region is not just about ground shaking. It is about the full range of hazards that a follow-up rupture could produce. And some of those hazards are directly relevant to the Fukushima site in ways that today's event was not. Consider the tsunami earthquake scenario. We discussed this earlier in the context of the shallow updip fault zone, the segment of the Japan Trench closest to the seafloor surface, the one that did not appear to rupture today, the one that produces disproportionately large ocean waves relative to the shaking felt on land. A tsunami earthquake on the Sanriku Gap, if it occurred, could generate waves significantly larger than the ones that arrived today. The 2011 tsunami, which was produced by a far larger and shallower rupture than today's event, sent waves of up to 14 meters crashing into the Fukushima seawalls. Those seawalls have since been reinforced and raised. But the reinforcement was designed around the 2011 event as a reference case. A tsunami earthquake on a shallow segment, producing waves that behave differently from a standard megathrust tsunami, is not a scenario that any engineering standard can claim to have fully accounted for. The honest answer is that nobody knows exactly how the current infrastructure would respond to a worst-case shallow rupture on this segment. The engineers have modelled it. The models suggest the site would remain protected, but models are not the same as certainty. And after 2011, the gap between models and reality has a specific, painful shape, in the memory of everyone who works in nuclear safety in Japan. Or consider a rupture on an adjacent segment producing ground shaking more intense than today's event. The Fukushima site is built to withstand a specific design basis earthquake, a level of shaking that represents the worst case the engineers anticipated when the plant was constructed and subsequently revised upward after 2011. A sufficiently large and close rupture could, in principle, produce shaking that approaches or exceeds that design basis. The probability of that specific scenario over the next 7 days is low, but low is not zero. And in the context of a site that is in the middle of a decades-long decommissioning process involving highly radioactive material, low probability does not mean low consequence. For now, the message from the technical agencies is consistent and based on available evidence credible. No damage, no leaks, no elevated radiation readings, the plant is stable. But it is stable in a region where the probability of another major earthquake has just increased tenfold. where a formal government advisory is in place for the next 7 days, and where the specific failure scenarios most relevant to nuclear safety, large tsunamis, intense ground shaking, are precisely the scenarios the advisory exists to acknowledge as possibilities. That context does not change the current status, but it is the context in which the current status has to be understood. Stable today, under a tenfold elevated risk, is a different kind of stable than stable on a normal Tuesday. Now, having said all of that, having been precise about what the evidence shows and what it does not show, about what the risks are and what they are not, I want to turn to the other category of reaction that follows any major earthquake on this coast. Because alongside the legitimate concerns about Fukushima, alongside the carefully calibrated language of the scientific advisory, alongside the real and serious questions that geophysicists are losing sleep over tonight, there is another layer of response, one that is louder, faster, and considerably less interested in what the evidence actually says. Within hours of any major earthquake in Japan, certain corners of the internet fill up with a very specific kind of content. Claims that the earthquake was not natural, that it was triggered artificially, that a weapon was used, that a government caused it, that the timing is too convenient to be coincidental. These claims spread faster than seismic waves and are considerably harder to stop. And while I have no interest in amplifying them, I do think they deserve a direct and honest response. Because the people who share them are not all acting in bad faith. Some of them are genuinely frightened, genuinely uncertain, and genuinely trying to make sense of an event that feels too large and too sudden to be purely natural. That impulse is human. The conclusions it leads to in this case are wrong, and here is exactly why. Part 17. Conspiracies versus real triggers. Within hours of any major earthquake, certain corners of the internet fill up with claims about artificial triggering, weapons, weather modification programs, secret military projects, deep state operations, HAARP, directed energy, tectonic warfare. The specific terminology shifts with the news cycle and the platform, but the underlying claim is always the same, that the earthquake was not natural, that someone caused it, that the timing is too convenient, the location too significant, the scale too dramatic to be purely the result of geological processes that have been running for 400 million years without anyone's assistance. I want to be straightforward with you about how I approach this because I think you deserve honesty rather than performance. This channel, Project Nightwatch, covers fringe theories. We cover unexplained phenomena. We cover ideas that mainstream science does not always want to touch. That is part of what we do here, and I am not going to pretend otherwise. But covering fringe ideas seriously means applying the same standard to all of them. It means asking what the evidence actually shows. It means being willing to say, clearly and without hedging, when a claim fails the basic test of physical plausibility. And the claim that today's earthquake was artificially triggered fails that test. Not barely. Completely. Here is why. The energy released by a magnitude 7.7 earthquake is not an abstract number. It is approximately equivalent to the simultaneous detonation of several hundred of the largest nuclear weapons ever built by any nation in human history. The Tsar Bomba, the largest nuclear device ever detonated, released about 50 megatons of energy. A magnitude 7.7 releases the equivalent of roughly 300 to 400 of those devices fired simultaneously at a single point 30 kilometers below the seafloor. That is not a delivery problem that better engineering could solve. That is a physical impossibility given any technology that exists or has ever been proposed to exist on Earth. There is no weapon system, no directed energy platform, no classified military project in any nation's known or rumoured development pipeline that comes within several orders of magnitude of that energy delivery requirement. The physics does not work. The engineering does not exist. And the claim has never, in decades of serious investigation by people who would genuinely like to find evidence of it, produced a single credible piece of supporting data. The HAARP facility in Alaska is probably the most frequently cited culprit in earthquake conspiracy theories, so let me address it directly. HAARP, the High Frequency Active Auroral Research Program, is a real facility. It studies the ionosphere by transmitting radio waves into the upper atmosphere. Its total transmitter power is about 3.6 megawatts. That is roughly equivalent to a large commercial radio station. The energy required to trigger a subduction zone earthquake is, as we just discussed, hundreds of millions of times larger than that. HAARP cannot trigger earthquakes, not because it is a cover story, but because it is a radio transmitter, and radio transmitters do not move tectonic plates. Blaming HAARP for a magnitude 7.7 earthquake is the physical equivalent of blaming a flashlight for a solar flare. The category of object is simply wrong. Weather modification programs, cloud seeding, atmospheric manipulation. These are also real technologies, and some of them have genuine environmental implications worth discussing seriously. But weather modification operates in the troposphere, the lowest layer of the atmosphere, at altitudes measured in kilometres. The rupture today occurred 30 kilometres below the seafloor. The mechanism by which an atmospheric intervention could transmit enough energy downward through the ocean, through kilometres of sediment and oceanic crust, and into the locked fault interface of a subduction zone to trigger a rupture has never been proposed in any credible physical framework. Because there is no such mechanism, atmosphere and deep crustal geology are not connected in the way these theories require them to be. So what did cause today's earthquake? The answer is genuinely interesting, and it does not require any external agency to be dramatic. The Pacific Plate has been grinding westward and downward beneath the Okhotsk Plate at a rate of 8 to 9 centimeters per year for millions of years. Along the Japan Trench, that motion is not smooth. The two plates lock together along their contact surface, building up elastic strain the way a compressed spring builds up potential energy. When the accumulated strain exceeds the frictional resistance holding the plates together, the fault slips. The stored energy releases in seconds. That is an earthquake. The specific stress state of the Iwateoki segment tonight was shaped by 15 years of post-2011 stress redistribution, by 3 weeks of precursory activity, and by the slow, inexorable accumulation of tectonic loading that has been ongoing since before the first human being walked across the land bridge into the Americas. No external trigger required, no hidden agency, just physics, running on geological time, occasionally producing events that reshape coastlines and rewrite history. The real triggers for earthquakes are well understood, even if their precise timing is not. Tectonic stress accumulation is the primary driver. Poor fluid pressure changes, where water moving through fault zones reduces friction and can accelerate slip, are a secondary factor in some events. Coulomb stress transfer from previous earthquakes, which is central to understanding tonight's event in the context of 2011, is another well-documented mechanism. Tidal loading, the small but measurable stress changes produced by the gravitational pull of the Moon and Sun, has been shown to have a weak statistical influence on seismicity in some fault systems, and human-induced seismicity is real. Fluid injection from wastewater disposal wells has triggered earthquakes in Oklahoma and other regions, and reservoir impoundment has caused seismicity in multiple countries. But these human-induced events are small, magnitude 3, 4, occasionally 5, not magnitude 7.7 megathrust ruptures on subduction zones that extend hundreds of kilometers into the mantle. The scale difference is not a detail, it is the entire argument. Now, I mentioned space weather, and I want to spend a moment on this specifically because it is a subject this channel takes seriously, and because I think intellectual honesty requires me to address it directly, rather than lumping it in with HAARP theories and moving on. Solar activity, geomagnetic storms, cosmic ray flux, these are real physical phenomena with real effects on Earth systems. We cover them here because they matter. They affect satellite operations, power grids, communications infrastructure, human health in ways that are still being studied. The question of whether they influence seismicity is a legitimate scientific question, and it has been studied by legitimate researchers. The honest answer is, probably not in any meaningful way, and definitely not in this case. Some studies have found weak statistical correlations between certain space weather conditions and small increases in seismicity. Those correlations are inconsistent across different fault systems and different time periods. The proposed physical mechanisms, electromagnetic coupling to the crust, changes in ionospheric electric fields, cosmic ray ionization of groundwater, are speculative and not well supported by the data. The scientific consensus, to the extent one exists, is that space weather effects on earthquake occurrence are negligible compared to tectonic stress accumulation. And at the time of today's earthquake, solar activity was relatively quiet. No major geomagnetic storm was in progress. No significant solar energetic particle event had occurred in the preceding days. Whatever role space weather plays in seismicity in general, and that role is small, it played no identifiable role in tonight's rupture. The earthquake was, by every available measure, a purely natural consequence of the stress state of the Japan Trench. I say all of this not to mock the people who ask these questions, because I think most of them are asking out of genuine confusion and genuine fear, and those are human responses to a terrifying event. I say it because the conspiracy narrative, however understandable its emotional roots, actively redirects attention away from the things that actually matter right now. Every minute spent debating whether HAARP caused tonight's earthquake is a minute not spent understanding the GPS data that will tell us whether afterslip is migrating toward the shallow updip zone. Every share of a tectonic weapon theory is a piece of bandwidth that could have carried information about evacuation routes or the actual probability framework behind the megaquake advisory. The noise of speculation is not harmless. It competes with signal. And in a situation where the signal is already difficult enough to read clearly, that competition has real costs. Natural stress processes, not external forces, will determine whether this sequence escalates over the next 7 days. That is the honest framing. The fault will do what the fault will do, driven by physics that has been running longer than our species has existed, indifferent to our theories and our fears and our need to assign agency to events that have none. The GPS stations will record what they record. The aftershocks will occur where they occur. The stress will migrate where it migrates. And the only way to understand what is coming, to whatever limited degree understanding is possible, is to watch those signals clearly without the distortion of narratives that feel satisfying but lead nowhere true. Which returns us finally to the central question, the one that has been present in every section of tonight's story, the one that the advisory acknowledges without answering, the one that the data raises without resolving, the one that hangs over every GPS reading and every aftershock magnitude, and every millimetre of ground deformation being recorded right now along the northeastern coast of Japan. Was today the main event, or was it the foreshock? And the answer, still, is that we do not know. Part 18. Main shock versus foreshock. The distinction between a main shock and a foreshock is, as we have discussed, only meaningful in retrospect. Before a larger event occurs, every earthquake is, by definition, a main shock. It becomes a foreshock only when something bigger comes along to redefine it. And the terrifying implication of that fact, the one that I want you to sit with for a moment, because it is not a rhetorical flourish, it is a literal description of how the science works, is that we cannot currently tell in real time which category today's earthquake belongs to. The instruments cannot tell us. The models cannot tell us. The scientists who have spent their entire careers studying this specific fault cannot tell us. Not because they are not good enough at their jobs, but because the information required to make that determination does not yet exist. It will only exist after the fact, and after the fact is precisely when it stops mattering. This is worth dwelling on because I think it is the single most important concept for understanding why tonight's situation is as serious as it is. We are not dealing with a known unknown, where we understand the shape of our ignorance and can bound it with confidence intervals. We are dealing with a system that is, at this specific moment, genuinely unresolved. The fault has moved, the stress field has changed, the probability distribution of outcomes has shifted. And the new distribution, the one that includes the foreshock scenario at elevated frequency, cannot be collapsed back down to a single answer until the system itself provides one, either by producing another large earthquake or by decaying quietly back to background. Those are the only two ways this resolves, and right now we are suspended between them. The evidence we have at this moment is ambiguous in a way that is almost frustrating in its completeness. Every single piece of data we have examined tonight points in two directions simultaneously. The magnitude, 7.7, is large but not unprecedented on this fault system. It is consistent with a complete stress release on the Iwate-Oki segment. It is also consistent with a partial release that leaves significant stress available for a follow-up event. Both readings of the same number. The tsunami, smaller than forecast, suggesting a deep rupture, is consistent with a normal main shock that released stress primarily on the deep, strongly coupled portion of the fault interface. It is also consistent with an incomplete rupture that left the shallow updip zone, the zone that produces tsunami earthquakes, more stressed than before. Both readings of the same wave height. The aftershock sequence, slightly below the magnitude expected under Barth's law, is consistent with a sequence still in its early decay phase, that will eventually produce a larger aftershock and then taper off normally. It is also consistent with a sequence that has not yet produced its largest member, because the largest member will not be an aftershock at all, but a separate rupture on an adjacent segment. Both readings of the same pattern. The geographic location is the most pointed piece of ambiguity of all. Today's rupture occurred exactly where post-2011 stress models predicted elevated risk. Exactly on the segment that multiple independent research teams, publishing in peer-reviewed journals over the past decade, identified as the most likely candidate for the next major rupture on the northern Japan Trench. That is either deeply reassuring or deeply unsettling, depending on which interpretation you apply. The reassuring reading is that the models worked. The stress that had been accumulating in this segment since 2011 has now been released, the prediction was vindicated, and the system can begin its long process of returning to equilibrium. The unsettling reading is that the same models which predicted this segment would fail also predict that a partial failure on this segment transfers stress further to the shallow up-dip zone, to the adjacent segments to the north and south, to the parts of the fault that did not move today. Both readings come from the same models. Both are physically plausible, and the data does not currently discriminate between them. This is the fundamental frustration of real-time seismology, and I want to be honest with you about how deep that frustration runs among the people doing this work. Because there is a version of this story that the media sometimes tells, where the scientists are the calm, authoritative voices who know what is happening and are carefully managing the release of information to a nervous public. That version is comforting. It is also not entirely accurate. The scientists monitoring this fault tonight are not withholding a clear answer because they are being cautious about public communication. They are not withholding a clear answer because they have one and have decided not to share it yet. They do not have a clear answer. They are staring at the same ambiguous data that I have been walking you through, running it through the best models available, and arriving at the same uncomfortable conclusion. The system we are trying to read does not give clean signals. It gives overlapping, ambiguous, context-dependent signatures that can only be fully interpreted after the fact. The scientists know this better than anyone, and that knowledge, rather than providing comfort, is precisely what is keeping them awake. The uncertainty here is not the ordinary uncertainty of a coin flip, where you do not know the outcome but you know the probabilities exactly. It is a deeper kind of uncertainty, the kind where even the probabilities themselves are estimates, built on incomplete models of a system we only partially understand, calibrated against a historical record that is too short to capture the full range of possible behaviours on a fault that operates on timescales of centuries. When the JMA says 1% probability of a magnitude 8 or larger in the next 7 days, that number is not a precise calculation derived from first principles. It is an informed estimate produced by combining multiple models, incorporating multiple sources of uncertainty, and expressing the result in a form that is communicable to the public. It could be 0.5%, it could be 2%. The honest answer is that we do not know the probability precisely. We know it has increased substantially. We know it is elevated above normal. We do not know by exactly how much or for exactly how long, or what specific form the elevated risk will take if it materializes. What we can say, with genuine confidence, is this. The most likely outcome, statistically, is that today's earthquake was the main event. This is not wishful thinking. It is a statement grounded in the global historical record of large subduction earthquakes. Most magnitude 7.7 earthquakes are not followed by larger events. The majority of aftershock sequences decay along roughly predictable lines, with the largest aftershock falling within the range Bath's law would suggest, the frequency of aftershocks tapering according to modified Omori's law, and the region gradually returning to background seismicity over weeks to months. That is the base rate. That is what happens most of the time, and most of the time is a meaningful category, not a dismissal of risk, but probably is not certainly. And this event is not an average magnitude 7.7 somewhere in the world. It is a magnitude 7.7 on a specific segment of a specific fault system that has been stress-loaded for 15 years by the largest earthquake in Japan's recorded modern history. It occurred on a segment that was specifically identified in the published scientific literature as elevated risk before today's event. It produced a smaller than expected tsunami, suggesting the shallow updip zone may not have ruptured. It generated an aftershock sequence that is, so far running slightly below typical magnitude expectations. Every one of those contextual factors pushes the probability of the foreshock scenario above the global baseline for a magnitude 7.7, not above 50%, probably not above 10%, but meaningfully above the 1 to 2% range that would apply to a comparable earthquake in a less specifically concerning context. And when the consequence side of the equation is a potential magnitude 8 or 9 rupture on one of the most densely populated coastlines on Earth, even a small elevation in probability demands serious attention. There is also the psychological dimension of this, which I do not want to gloss over, because I think it is real and it matters. The people who live in the 182 municipalities covered by the advisory are not probability calculators. They are human beings who in many cases survived 2011, who lost family members or neighbours or homes, who rebuilt their lives in the shadow of a disaster that the entire world watched unfold in real time. When those people receive a megaquake advisory tonight, they are not processing a statistical shift in a probability distribution. They are processing the possibility that it might happen again, that the thing they survived once might be asking for a second attempt. The advisory is designed to inform, but information lands in a human context, and the human context along this coastline is one of the most traumatized in the world. The central question, tonight and for the next 7 days, is whether this particular earthquake will turn out to belong to the vast majority of large earthquakes that are the main event, that release their stress and decay and leave the region quieter than before, or to the small, historically documented, physically plausible minority that are the warning shot, the opening statement of a longer sentence, the whisper before the scream, and the only way to find out, the only epistemically honest answer available to science right now is to wait. To watch the GPS stations, to monitor the aftershock sequence, to track the afterslip behaviour over the next 72 hours, to pay attention to every signal the fault sends, knowing that the fault sent no signal at all before it moved today, and to hold in parallel both the most likely outcome and the worst case scenario, not because they are equally probable, but because the gap between them is the gap between a news cycle and a catastrophe. And we do not yet know which side of that gap we are on. Part 19, the next 7 days. The advisory is active until April 27th, 1 week from today. 7 days during which the probability of a catastrophic earthquake in the region is elevated approximately tenfold above baseline. During those 7 days, the scientific community will be watching the fault with every instrument available. GPS stations will be recording ground motion in real time. Seismic networks will be monitoring aftershocks and any unusual activity. Seafloor sensors will be tracking ocean bottom pressure, which can detect tsunami initiation before waves reach the coast. Satellite data will be analysed for any signs of surface deformation. The data will flow in continuously, and analysts will be trying to read in real time what the system is doing. The decisions that will be made based on that data are decisions that affect tens of millions of people. Whether to extend the advisory beyond the initial 7-day window, whether to raise or lower the alert level, whether to order additional evacuations, whether to restrict access to coastal areas. These decisions are being made right now and over the coming days by a community of scientists, public officials, and emergency managers operating under enormous pressure with incomplete information in a system where the cost of being wrong in either direction is significant. 2 scenarios dominate the next 7 days. Let me walk through both. In the first scenario, the sequence decays normally. Aftershocks continue, following the typical pattern of decreasing frequency and magnitude. The largest aftershock, whenever it occurs, falls within the range predicted by Barth's law. Afterslip, measured by GPS, concentrates on the deep portion of the fault interface and slowly tapers off over the coming weeks. No major ruptures occur on adjacent segments. The advisory expires on April 27th without incident. The region enters a period of relative quiet, and today's earthquake is logged in the historical record as a significant but isolated event. The 182 municipalities return to normal life. The scientific community analyzes the data for years, refining models, adding this event to the growing database of subduction zone behaviour. That is the most likely outcome. That is the outcome we should all hope for. In the second scenario, the sequence escalates. A larger event occurs within the advisory window. It could be another deep rupture on an adjacent segment. It could be a shallow updip rupture producing a tsunami earthquake. It could be something truly catastrophic, a full megathrust event rivaling or exceeding 2011. The specific form the escalation takes would depend on where, exactly, the next rupture initiates and how it propagates. In all cases, the consequences would be severe: tsunamis, ground shaking, infrastructure damage, loss of life. The scenarios are not equivalent to each other, but all of them represent outcomes that the current level of preparation in northern Japan is, at best, partially equipped to handle. Is what happened today the main event, or is it the foreshock? That is the question a week from now will have answered, one way or the other. If the advisory expires without further major events, the answer will be main shock. If another large earthquake occurs, the answer will be foreshock. There is no third option. There is no outcome in which the question remains permanently open. The system will resolve itself, in one direction or the other, within a bounded time frame. What residents of the affected region are being asked to do in the meantime is not panic. It is prepare. Know your evacuation route, keep emergency supplies ready, pay attention to official communications, stay away from coastal areas without compelling reason. Do not dismiss the advisory as alarmism. Do not treat it as a prediction that something will happen. Treat it as what it is. An acknowledgement that the system has shifted, that the coming week is different from a normal week, and that vigilance is warranted. A week from now, we will know what this was. The advisory will either have expired quietly, and the question will be answered, or it will have been fulfilled, and the question will have been answered in a much more painful way. Either way, the answer will come, and we will move forward with whatever knowledge the next 7 days provide, into the longer arc of understanding what the Japan Trench is doing, how it will continue to evolve, and what, if anything, we can ever hope to predict about the rare events that reshape the geography of coastlines and the history of nations. For now, the earthquake has happened. The tsunami has come and gone, smaller than feared. The aftershocks are continuing, the advisory is in place, and 172,000 people along a 1,000-kilometre stretch of coastline are waking up tomorrow to a different kind of morning than they were expecting yesterday. A morning in which the ground beneath their feet is, statistically, more likely to rupture than it was a week ago. A morning in which the science, honestly and carefully, cannot tell them whether anything else is coming. A morning in which all they can do is wait and watch and prepare, while the fault system that feeds them, shelters them, and occasionally tries to kill them continues its slow, inexorable grinding beneath the Pacific. This is Project Nightwatch. The system has shifted, the outcome is unresolved, and somewhere, 30 kilometers below the surface of the sea, the rock is still moving. The question is not whether it will move again. The question is when, and how big, and whether the people who study it for a living, who have given their careers to reading its signals, will have any warning at all before it does. A week from now, we will know what this was. Until then, the ground waits, and so do we.